So today the plan is we're going to cover nonparametric Bayesian inference, because we've done nonparametric density estimation, nonparametric classification, nonparametric regression, all from the frequentist point of view. And so today we want to cover nonparametric estimation from the Bayesian point of view. And then on Thursday's class, remember we have a guest lecture. Sivaraman Balakrishnan is going to come and talk about boosting. And he's going to talk about it, again, from a very different point of view than the way it's covered in my notes. So you should probably look at my notes, which are the more statistical version that treats boosting as kind of a forward stepwise regression type of thing. He's going to talk about it more from its original PAC learning point of view. So you'll get a different point of view on that. All right, so let's talk about nonparametric Bayes. Any questions before I start? Okay, how many of you have done any nonparametric Bayesian stuff? Okay, not many. Good. I mean, not good. Good in the sense that I have something interesting to tell you, I guess. Oh, I'm going to have to reinstate my rule of locking the door at 1:30 if you guys don't get here sooner. Plus, you're on, everybody can see you on YouTube coming in late. Your parents and your brothers and sisters are watching you come into class late, so it's very embarrassing. All right. All right, so nonparametric Bayesian inference. We talked about Bayesian inference in 705, but in principle, we can also do nonparametric stuff using the Bayesian methods, although we only did the parametric case in 705. But we have to think about what does that mean, because when we talk about nonparametric inference, we're talking about doing inference for a classifier or a regression function or a density function. These are not things that are characterized by a finite set of parameters, which is why we call them nonparametric. So what does it mean to put a prior on a space of functions, like on a Sobolev space? And what does it mean to get a posterior? And how do we compute these things? And most importantly, what are the properties? When you have a nonparametric posterior distribution, is it consistent? Does it converge to the true function and so on? These are actually very delicate and subtle issues. So let's just remind ourselves, if we were just doing simple parametric inference, we know how the machinery works for Bayesian inference. We would have a posterior distribution given, let's call it y. Here y will be our vector of data. These are drawn from some unknown distribution p. And we just did Bayes' theorem, which was just to multiply the prior times the likelihood. And then there's a normalizing constant here. In the notes, I called it m of y. This is just some prior over the parameter, typically a smooth prior. L is just the usual likelihood function, which, if the data are IID, would look something like this. And, it's all pretty straightforward, right? This is, computing it can be difficult, but many of you have seen in some of your courses MCMC methods, Markov chain Monte Carlo methods, which show that even if I can't explicitly compute this, I can usually draw samples from it in some way, although that can be challenging, but it's often doable. So the computational issues have gotten much more manageable. But now let's turn to nonparametric inference. So let's think about estimating a function. Let's think, for example, about the density estimation problem. So now I have y1 to yn are a sample from some density. The density is going to be in some function space. So it can't be described by just a few parameters. It's going to live in this function space. Oh, we got some more late people. Let's shame them. Actually, the best thing I could probably do is I should have Jisoo here, and every time you come in late, he takes off 10 points from your final grade. That would get everybody to show up on time. It's the carrot versus the stick, and unfortunately, the stick often works much better. All right, so what's this going to be? Well, we saw, like in regression and density estimation, we can't usually take the set of functions that we're dealing with. We can't just assume it's any old function, except in certain cases, like when we did the cumulative distribution function. But for things like regression functions and so on, we had to make some sort of smoothness assumptions. So for example, Sobolev type assumptions were things like the set of all densities such that, let's say, the second derivative squared was less than some constant or was finite, things like of that nature, right? That's the kind of assumptions we had to make. If we do make that assumption, inference is possible, and we could compute the posterior probability. Now, you have to think about the parameter as the function. So I'm going to write pi n of a, just for short. That means the posterior probability that f is in a given the data. So if this is my set f, for any set a, this is some arbitrary set a, we can consider what's the posterior probability. This is no different than here. I can talk about what's the posterior probability that theta is in a given y. It's just that it's a little bit more abstract because theta is now a function. And you have to somehow picture this is like a set of functions. Picture some sort of distribution over here, which will be the posterior distribution. And in principle, we can compute the posterior probability. In fact, if there are densities, we can just use Bayes' rule, which is just to integrate the likelihood. Yeah, let's write it like this. The likelihood integrated with respect to some prior. This is like likelihood times prior over the set A divided by the normalizing constant. So at least symbolically, it looks the same as in the parametric case. I'm just taking the likelihood times the prior over the space and integrating it over A and getting the posterior probability. Now, there are some complications here. I've just used Bayes' rule. It turns out in a non-parametric situation, you can't always use Bayes' rule. There's certain conditions you need for Bayes' rule. So this is a subtle point, that the posterior distribution, the distribution of the function given the data, is always well defined. But whether you can write this formula, which is Bayes' rule, that may or may not be true. It turns out Bayes' rule to get the posterior, you think of them in the parametric world as the same thing. Getting the posterior is applying Bayes' theorem. It's not true in the non-parametric world. The posterior can perfectly well exist, even though you might not be able to use Bayes' rule. So the way to think about that is the prior defines a distribution on theta, and then the distribution f defines a distribution of the data given theta. So if I give you a distribution of theta and I give you a distribution of y given theta, that defines some sort of joint distribution for y and theta. And then when I have a joint distribution, I can always talk about the conditional distribution. So the conditional distribution will be well defined. The mechanism to get there may or may not be Bayes' theorem. So that's a very subtle point. I don't want to spend a lot of time on it. This is something like in a measured theoretic probability course, you would talk about this kind of thing. But luckily, we're going to see, even if we can't use Bayes' theorem, we can often still compute the posterior indirectly. It's kind of surprising, maybe.
I'm sorry, I know you just say you don't want to go on with this, but I mean, isn't Bayes' theorem just like an immediate consequence of the definition of the conditional distribution?
No, it's not. So the technical condition is that the set of things we're dealing with have to be dominated by something called a sigma finite measure. And you can have models where that's just simply not true. And so the posterior may be well defined, even though you can't write it as likelihood times prior. Let's not worry too much about it. Okay, we'll come back to this point later as needed. The only reason why I'm mentioning it is because we're going to compute posteriors. In fact, people often compute posteriors in cases where they can't write it as likelihood times prior. So we'll see that as we move along.
How do you construct a prior?
We're going to talk about that in detail. That's a good question. How do we even construct a... So yeah, I have this list of questions on page 2, which is how do we construct a prior? Exactly the question you just asked me. How do we construct a prior on an infinite dimensional space? How do we compute the posterior? Or another way to say it is typically we're not going to compute it. We're probably going to draw from the posterior, because sometimes we can't compute it, but as long as we can draw random samples from something, we kind of know the distribution. So we're probably going to resort to random sampling. And then really what I want to focus on, because these other issues are talked a lot about in other courses, I want to talk about the third question. What are the properties of this posterior? Is it consistent? If I give you more and more data, so here's a fundamental question. Suppose, there's a true distribution in here. I'm actually giving you samples from this. You compute this posterior however we compute it. Is it concentrating around the true thing? And this is a non-trivial question. So first I want to talk about constructing the priors, getting the posteriors, and then we'll talk about the theoretical properties. If we don't get to it all today, then I'm still going to have the guest lecture Thursday, and then we'll return to this on next Tuesday. There's a lot of interesting subtle issues here. So first of all, I'm only going to talk about 3 problems, but they span a wide range. So let me list the 3 problems that we're going to consider in these notes. So we're going to say what the problem is that we're studying. Then I want to say what is the frequentist approach to this problem. And then what is the nonparametric Bayesian approach. So the first problem is estimating a CDF, a cumulative distribution function. It's not usually a problem of interest in and of itself, but what we saw in 705 is often it's a first step towards solving another problem. If we can do that, it can help us solve other problems. Do you remember, how did we estimate that in 705? The empirical distribution. I'll remind you about that in a minute. In the Bayesian world, we use something called the Dirichlet process. That'll be the analog. This was invented by Tom, blanking on his name. Tom, does anybody know? Who invented the Dirichlet process? Somebody knows. His name will come back to me. Tom Ferguson, there it is. This was invented by Tom Ferguson, I'm going to say in the 70s, actually. So it actually goes back quite a ways. And we'll talk about what the differences are. Okay, then we'll talk about estimating a density. And then we had various ways of doing it. Probably the most common one is the kernel density estimator. And we saw, we know its properties. It's mean squared error, bias, variance, and all that stuff. The most common way of doing it in Bayesian inference is to use a Dirichlet process mixture. So Dirichlet process plays part of it, but there's an extra layer involved in the model. And then we'll talk about regression, nonparametric regression. Again, we saw many ways of doing that from the frequentist point of view. An example would be the kernel smoother. But we also saw there's reproducing kernel Hilbert space methods. There's local polynomial smoothers. I'm just giving a typical example. The most common approach in the Bayesian world is to use what's called Gaussian processes. Okay, so I'm just going to, what I'll do is explain in each case how it's done. And then at the end, come back and talk about the properties. And the properties you're going to see are a little bit surprising. They're not so immediate. In frequentist and Bayesian inference for parametric models, as long as you're dealing with fairly regular models and smooth priors, there isn't much difference. At least, once n gets large, the Bayesian methods and the frequentist methods end up being very, very similar. That's something we talked about in 705. That's not true in nonparametric inference. And the reason is because we're dealing with infinite dimensional spaces, or intuitively, we're dealing with, think of parametric models with many, many parameters. Then the Bayesian methods and the frequentist methods can be very different. So let's start with this first problem. I want to estimate a CDF on the real line. So we have x1 to xn are drawn from some unknown CDF. A CDF, you remember, this is something that looks like this. And the way we solved this problem was with the empirical. So we take our data points and we put a mass of 1 over n at each data point and then compute the corresponding CDF. And what does that correspond to? That's just this It's just the CDF that jumps by 1 over n at each data point, right? So it looked like this. It was 0, then it jumps to 1 over n, then it jumps to 2 over n, then it jumps to 3 over n, and so on. It goes up like this. And so that's our empirical distribution. And we saw that there was some nice properties of this thing. Remember, we had an inequality, kind of a VC type inequality. The particular one I'm going to write down is actually called the DKW inequality, different letters, but it's basically like a VC inequality, which says that the probability that the maximum difference between the estimated CDF and the true CDF is bigger than epsilon is less than or equal to 2e to the minus 2n epsilon squared. So that tells us that the probability that these differ anywhere is very, very small. Goes to 0 very quickly, exponentially fast. Okay, so hopefully you remember that. So that's a justification for using the empirical distribution function. And that implies also that it's consistent, that the maximum difference, therefore, is going to 0 in probability. But it also gives us a confidence band, because if I set this equal to alpha, say I want a confidence level of 1 minus alpha, just set the probability of an error to be alpha. So if I set this equal to alpha and solve, we get epsilon is 1 over 2n times log of 2 over alpha, square root. So if I choose that particular epsilon, I should probably call it epsilon n, because it depends on n, then the probability that these differ by more than that thing is less than alpha by construction. What that means is if I set a function, let's say L of x to be fn of x minus epsilon, and u of x to be fn of x plus epsilon, then the probability that L is less than f is less than u, the probability that these two functions trap f, and this is uniform over x, so this is for all x, is at least 1 minus alpha. So in other words, if I add and subtract epsilon here, I get a confidence band which traps the true CDF 95% of the time, or 1 minus alpha percent of the time. In fact, it's worth pointing out that this confidence set, this statement, is true uniformly over x, but it's true for every single distribution. I didn't assume anything about the distribution. So we can actually say that the info over every distribution of the probability that this statement holds is bigger than 1 minus alpha. So it's true uniformly over x and uniformly over all distributions. So that's a pretty complete way of estimating a CDF. We have a point estimator, we have a confidence band. Yes?
So I mean, we don't really see such easiness with densities or anything else. So is the reason for this easiness the fact that the CDF itself is distributed as a uniform?
No. So why is it so easy to do? So things are definitely going to get more complicated for regression and density estimate. Why is it so easy to do CDFs? Well, the CDF, remember, is just counting the probability to the left of a number over a set. And that collection of set, the CDF is the probability of the set minus infinity up to x. And that collection of sets has a finite VC dimension. That's what makes estimating a CDF easy. There's no connection when we get to density estimation regression with such simple quantities. It does work in multiple dimensions, but it's a different inequality, and a dimension comes into it. Okay, so that's the frequentist solution. Any other questions? Let's now turn to the Bayesian solution, which is somewhat different. So the first question I have to address, and this was Tom Ferguson's great insight, which is how do I put a prior on the space of all CDFs? So if I take F to be the set of all CDFs, that's a pretty big class of functions. How do I construct a prior? So here's the point of view we have to take. What does it mean to say I've constructed a prior? Let's go back to parametric inference. Suppose I had a real valued parameter, and I told you, oh, my prior is, I'm going to use a normal with some mean and some variance. So I've constructed a prior. What does that mean? Well, I've told you the distribution. You could write down the density, for example. But there's another sense in which I can say I've constructed a prior, is suppose I tell you I have an algorithm for drawing from the prior distribution. I don't have a formula for the prior distribution, but suppose I had an algorithm. I could draw as many observations as I want from the prior distribution using a certain algorithm. In that sense, you know the prior. That's another sense of saying I have a distribution. If I can draw an infinite sample from a distribution, then there's a sense in which you know that distribution. So for example, suppose you never learned the formula for a normal, but you did have an algorithm that could draw as many observations as you wanted from a normal. Then you could say you know that prior. You know that distribution. Okay, is that all right? That knowing how to draw from it is in some sense equivalent to knowing the distribution in some sense. And that's how I'm going to describe pi, is I'm not going to describe a formula for pi. I'm going to describe an algorithm for how to draw from it. And what do I mean by drawing? I mean drawing a random distribution function. So we're going to draw a random distribution from this prior. And I'm going to give you an algorithm for doing that. And in that sense, I'm describing what the prior is. Okay, so it's kind of an indirect description of the prior. All right, here's the prior is called a Dirichlet process. And, you know, priors often have parameters in them too. Like if I tell you that theta has a normal, I still have to tell you the mean and the variance. Or if I tell you it's a beta, I have to specify these hyperparameters. So the Dirichlet process itself has two hyperparameters. One of them is a function. It's another CDF. You can think of this as your prior guess at the CDF. Okay, and then there's another parameter. Actually, in the notes, I'd put them in the other order. So there's this is a number alpha, and this is a function, a CDF. So to specify this prior, you must specify a CDF and a number. Yes?
Is there an interpretation of this CDF as like the mean of the prior?
Yes, it's the mean of the prior. And this controls how concentrated the prior is around the mean. That's exactly right.
What is this Dirichlet here? Is it a distribution?
It's a distribution on the space of all distribution functions. I shouldn't call it Dirichlet, I should call it Dirichlet process. Okay.
So it's not the Dirichlet distribution.
There's a connection to that, but it's not that. Yes. Okay? So I'm now going to describe this distribution, which lives on the set of all distribution functions, I'm just going to tell you how to draw from it. How would I draw, just like here, if I told you, how would I draw a theta from this distribution? Well, I could give you an algorithm for doing it. How would I draw a random distribution from this Dirichlet process? Okay? And it's 4 steps. Okay? So first, I draw an infinite sequence, IID, from this base measure. Now, of course, you could never draw an infinite sequence, so just think of drawing a million. Okay? But theoretically, imagine drawing an infinite sequence. That's step 1. Now, step 2 is to draw another infinite sequence of random variables from a beta distribution with parameters 1 and alpha. Let's remind ourselves, what does a beta distribution? In general, a beta distribution, say with parameters a and b, has a density of the form x to the a minus 1, 1 minus x to the b minus 1. So in this case, this term disappears, and so this is like 1 minus x to the beta. So I guess this looks like something like this. It's some density on 0, 1. And I draw an infinite sequence. Okay? Now the third step is called the stick breaking step. Stick breaking. People who work in this area like making up funny names. So there's the stick breaking process. There's something called the Chinese restaurant process, the Indian buffet process. There's all these, I didn't make up these names. What's the stick breaking process? Let me draw a picture of it, and then I'll write the formula for it. What you do is you start with a stick of length 1. And now we break off a piece of that stick called W1. And W1 is just V1. So remember, V1 is from a beta, so it's going to be a number between 0 and 1. Okay, so let's suppose it's here. So I'm taking this piece of the stick. This is W1. And I'm setting it aside. Now, all I do is I take the second, to get the second, I'm going to get W2. W2 is, I just take the second beta, which is a number between 0 and 1, and I take that fraction of what's remaining of the stick. I want to pull that piece off. So what is that? That's V2 times 1 minus V1. 1 minus V1 is the remaining part of the stick, and I take that fraction of it. So that's W2. And now I repeat. I take what's left, and my third one is V3 times, I guess it's going to be 1 minus V1, 1 minus V2, and so on. I just keep, as it implies, I keep breaking off pieces of the stick, and the amount I take each time, the fraction I take each time of the remaining stick is just given by those beta random variables. So that gives me a new set of random variables, W1, W2, W3, which, as you show in the homework, next homework, it adds up to 1. They add up to 1. They're non-negative numbers that add up to 1. That should make intuitive sense, right? Because I just keep breaking off pieces of this unit stick. Okay, the fourth step is finally to construct the CDF. And let me draw a picture of it first. Here's the real line. I'm going to show you the CDF. You take these S's, which I call seeds, that's why I call them S. Those are the locations that you're going to put some mass. So this is maybe S1, maybe S2 is over here, S3 is here. Again, there's infinitely many of these, but let's just pretend there's, I'm just going to draw like there's finitely many of these. And now what you do is you take these W's and you put some mass. I take this amount of mass and put it at the first point. So the amount of mass at S1 is W1. The amount of mass at S2 is W2, and so on. And you just keep placing these pieces of mass down. So mathematically, F is an infinite sum of weights, those W's, and this is a point mass. This is something which puts all its mass here. That's just a formula for what I just did. Or another way to say it is f of t is equal to the sum of all weights such that those seeds are less than t. So the actual CDF is going to be a very, very, very jumpy thing, right? It's discrete. It's not continuous. Let's see if I have a picture. Somewhere later on you'll see a picture. We'll get to that later. I have some pictures of a Dirichlet. That's one draw from this prior. So let me first make sure, is the algorithm clear? Any questions about the algorithm? In practice, we're not going to draw infinitely many things, obviously, but apart from that, is the steps clear?
Yes, so our output is a CDF, and this is like the last F.
The very last step is the CDF. That's the output. That constitutes a single draw from the prior. So now you know an algorithm to draw from this prior. So if you wanted to, you could repeat this process, say 1,000 times, and look at the CDFs you get out. And what are you looking at? You're looking at 1,000 draws from your prior, so you're kind of looking at your prior. That's how you're looking at the prior distribution. If you wanted to say, what does this prior look like? You just draw 1,000 random CDFs from your prior and plot them, and that gives you a feeling for where are they centered, how variable are they, and so on. Okay?
Is this the only approach to define a prior like this?
No. There's zillions of ways to define a prior on the space of CDFs, but this is the most common approach because it's very tractable, as we'll see. It has all kinds of properties people like. But just like even for a real valued random variable, how many ways are there of defining a prior? Well, there's infinite many ways, and it's the same with CDFs. But this is I would say, the most common one.
Is there any, like,
Oh yeah, I'm going to get to by looking at the properties of this thing, I hope we'll start to develop some intuition, like where did this come from, right? And so in particular, let's talk about the connection with the Dirichlet distribution. That was really, so the way I just defined it is not how it's defined in Tom Ferguson's paper, actually. Let's connect it to the way he did it. The reason why I like to describe it this way, this construction, I think it's due to Sethuraman. I like to describe that first because I think it's good to have a concrete algorithm for how you would actually draw from the distribution. I think that somehow makes it more concrete. But to understand what are the properties of this prior, we go back to Ferguson's original idea. So suppose I drew one of these things. What's it going to look like typically? And one way to answer that question is to say, well, suppose you drew a random CDF from this prior. Suppose I decide I want to look at some of the properties of this. I'm going to arbitrarily divide the real line into a finite partition. So let's call those things A1, A2, up to AK. Okay, I've just arbitrarily partitioned the real line into a finite number of sets. Now, you've just handed me your random distribution function, which was drawn from your prior. I can use that distribution function and say, how much probability does your distribution function put in each of these cells? Because I have a CDF, and I can just compute the amount of mass. In other words, I'm really just adding up those weights within each of these cells. So let's call that, what am I going to get? I'm going to get a vector, right? The amount of probability your randomly drawn F puts here is a number, and I'm going to do that. So I'm going to get a vector. I'm just going to call that F of A1. So just to recap, you drew a random distribution function. I said, how much mass does it place on these K sets? I've just arbitrarily constructed those K sets. And I compute that. It's a number, or it's a vector, right? It's a vector of real numbers. But now I can ask, if you repeatedly drew from your prior, what distribution would this vector have? Because think of this as a parameter. You know, this is like if I drew from a normal many times and I said, you know, how much probability does the normal put bigger than 1? I could draw repeatedly from the prior, and look at that probability. It's a random thing because the priors, from the point of view of the prior, this is a random distribution. This is a random vector. Well, the distribution is Dirichlet, as the name implies. Let me remind you what a Dirichlet is. So let me say that this has a just want to use the same notation I'm using in the notes. Has a Dirichlet distribution with parameter alpha, and I'm running out of symbols here. This is let's say V, where V is simply F0 where, what's a Dirichlet distribution? It's a density of the form. So this is because this is a vector now, it has it's just a regular old density. It has a density. Let me call this P. So the density for P is simply proportional to Pj to the alpha Vj minus 1, where this is the vector B. So what's a Dirichlet distribution, first of all? A Dirichlet distribution, if I only had two things, is a beta distribution. So the Dirichlet is just a multivariate generalization of the beta distribution. It's just a distribution on vectors that sum to 1. So if there was only two categories, this would just be a beta distribution. So that's just a generalization of the beta distribution. I think most of you have seen a Dirichlet distribution before. So what I'm saying is, if instead of looking at the whole function, which is some infinite dimensional creature, I just compute the probability content of a finite number of sets, that's now just a vector. And if I repeatedly drew, in fact, that vector lives on the simplex. The simplex, right, is a set of vectors that have to sum to 1. So that if I draw a simplex like this, every time I draw from your prior, I get an F, I compute this probability, I get a point on the simplex. If I were to repeatedly draw from the prior, I get a bunch of points. Eventually, I get a distribution. That distribution has a density, and the density is a Dirichlet distribution. That's what it is. And that's true no matter how I draw the partition. For any finite partition, the induced distribution I would get when you draw this F randomly is a Dirichlet distribution. That's why it's called a Dirichlet process. This is a common thing in the theory of probability, is when you have a probability measure defined on a complicated space, sometimes you define it in terms of how it behaves on finite things to describe its behavior. We're going to see the same thing when we talk about Gaussian processes. So this is actually how Ferguson defined the Dirichlet process. He said, I'm going to say a distribution has a Dirichlet process if whenever I draw from it randomly and evaluate it on a finite partition, it has this Dirichlet distribution. Then he had to show that there exist such distributions. The construction we did is kind of an explicit construction, and there's a theorem that one has to prove to show that the way I define things does actually give you this Dirichlet process, but it's true, that it's a fact. Okay, so there's two different ways to think about this Dirichlet process, either in terms of this algorithm for generating from the distribution, or it's just some way of drawing a random distribution function which has the property that when you look at some finite resolution, you get a Dirichlet distribution. I hope that helps somewhat with the intuition. I know these are abstract things, so it can be hard to picture what's going on, but why are we using a Dirichlet process?
No, if we draw F from the process, we will get a distribution.
Why is this true?
Yes.
Oh, well, it's a theorem. It's actually a matter of definition. The theorem is that this construction does have this property, so there's something to prove there. It's not obvious. Yeah.
What values can alpha take on? Is it greater than 0?
Greater than 0. Yeah, alpha is any positive number.
What is the relationship between Dirichlet process and Gaussian process?
They're quite different. So Gaussian processes are defined on certain classes of functions. The Dirichlet process is defined on CDFs. and they behave very differently. What they have in common is they're both ways of defining probability measures over spaces of functions. But it just turns out that for CDFs, this happens to be a useful, easy to work with distribution, and for regression, Gaussian processes turn out to be more useful. But these aren't the only ways to define priors, and there's lots of papers about defining priors in other ways.
But this definition doesn't give you a way to sample, right? So this
Yeah.
way-
So the nice thing about this is this tells you how to sample, right? This, in some sense, doesn't give you a way to sample, but it sort of does, because you could always divide the real line into some, pretty small, divide it into small pieces, and then just sample a Dirichlet and say, well, okay, what's going on in between I can't say much about, but I get some sort of approximate thing. So you can think of it almost like a way to draw from the distribution, but that's a more precise statement about that, yeah.
And how do you typically specify F0?
Well, now we're getting to this is always the question of Bayesian, is how do you specify the prior, right? I don't know. You have to ask someone who actually thinks these are useful. Okay, so. Sorry, I didn't mean to bias you there. Yeah, I mean, I seriously question whether you can specify F0 in a meaningful way, but that's just my opinion. I guess a more serious answer would be twofold, which would be if you have some sort of reliable scientific prior information about the CDF, you try to incorporate that by choosing a good F0. And asymptotically, as we'll see, the effect of the choice of F0 disappears as n goes to infinity. So that's a more serious answer to your question, I guess. But I do find the problem of how to specify, I don't have good answers to that question. I mean, so I have a friend named Zubin Garmani. Some of you might have heard of him. He's in England. And when I ask him this question, because he likes these things, he does what I said. He draws lots of distributions from the prior and looks at them and tries to decide, have I made a good choice for this problem? So he uses random sampling from the prior to try to assess whether he's made good choices of F0 and alpha.
If we follow this process, is it possible to get whatever distribution in that space we're considering?
Yes, every Dirichlet process is generated this way. And there are better computational methods, by the way. I described this because I think it's just concrete and easy to think about. But now the question becomes, let's suppose we've decided we're going to analyze our data this way. So here we go. I have a sample from an unknown CDF. Now I'm going to put my prior is going to be this Dirichlet process. Now the question is, what is the posterior? How do I compute the posterior? And here you cannot just write down a likelihood. Likelihoods require densities. We're not even assuming a density exists. These are discrete distributions, for example. So I can't multiply the likelihood times the prior. Nonetheless, as I said, that doesn't mean the posterior doesn't exist. In fact, it does exist. It's perfectly well defined. This is what Ferguson proved in his paper, was that the distribution of the unknown CDF given the data, the posterior distribution, is again a Dirichlet process. That's what makes these so convenient. It's conjugate. So you get another Dirichlet process, and the parameters, the parameter alpha gets changed to alpha plus n, and F0 gets replaced by, we'll call it F bar, and this is the posterior mean. This is the mean of this Dirichlet process. And what is it? It's n over n plus alpha times the empirical distribution function plus alpha over n plus alpha times our prior guess. So this is kind of a very intuitive thing. What we're doing is, this looks a lot like, remember the normal prior and normal likelihood, the posterior is normal. And the posterior mean was like a convex combination of the MLE and the prior mean. And the same thing is happening here. We're getting the empirical distribution, a combination of the empirical distribution and our prior guess. So that's something that's kind of satisfying. That's pretty neat. And you can see that when n gets large, this part starts to disappear, and the posterior mean gets closer and closer to the empirical distribution function. And now, if I asked you, okay, how do I deal with this posterior distribution? How do I look at the posterior? How do I find a 95% confidence, Bayesian confidence band? No problem. You just draw from the posterior many times using the same algorithm. The only thing that's changed is alpha was replaced by alpha plus n, f0 was replaced by f bar. But you use the same algorithm, and you can draw many times, let's say capital B times, from the posterior. So now you have, say, 10,000 randomly drawn CDFs from the posterior distribution. So you can plot them. You can look at what the posterior looks like in the sense of you can see what the posterior draws look like. You could also find a 95% Bayesian confidence band by finding two functions that trap 95% of the functions. So you could find an L and a U numerically so that the probability from the Bayesian point of view that L and U trap F given the data is, say, 1 minus alpha. But remember, this is a very different interpretation than the confidence band, right? This is saying, from the Bayesian point of view, the data are fixed. It's the CDF, our unknown, which is always treated as the random quantity. This is our degree of belief that F is trapped between L and U given Y1 to Yn. It doesn't mean in the frequentist sense that if I repeated the experiment over and over that you would trap the true F 95% of the time, right? That's the usual difference we talked about in 705 between Bayesian interpretation, which is about degrees of belief, and the frequentist interpretation, which is about coverage and long-run frequencies. So here's an example in figure 3 on page 7. What I'm showing you is I did a very small example, I think 25 observations. And first of all, I picked a particular Dirichlet process prior. This was just sort of arbitrary, just to show you pictures. So I picked alpha equals to 10, and I took f0 to be a normal. And I took a random draw from the prior, and I didn't plot the CDF up here. This is just the weights that came out. Okay? And the resulting CDF is shown on the right, along with the f0 that that smooth line is the f0, my prior guess of the CDF. And the jiggly line is just a typical random draw from the prior. Now I actually generated 25 observations from some distribution. And if you look at the bottom left, it says the blue line. I don't even see a blue line. But what you see is actually the bottom. Wait, what is it? The bottom left plot shows a few draws from the posterior. Oh yeah, it just didn't come out. Well, anyway, you can see some draws from the posterior. That's what those wiggly things are. There's the posterior mean that didn't show up very well there for some reason. And also there's one other line, which is the true CDF that I actually drew from. And then in the bottom right plot, I'm showing you, it's kind of hard to see it, but I've got the true CDF, the empirical CDF, the frequentist confidence band, and then the Bayesian posterior mean. It's quite a bit off in this case. Okay, so, yes?
Since averages from the Dirichlet prior is discrete, is there's a way to prove a continuous density from prior?
That's a good point. So the Dirichlet process the CDFs are always discrete. But people don't worry about that too much because it turns out if I take the set of CDFs, and while it's true that every time I draw a random CDF, say this one, that's a CDF, it's discrete, and another draw would be discrete. but it turns out it still has, they're arbitrarily close to, just like the rational numbers are arbitrarily close to the real numbers, it's dense. So people don't worry so much about that.
Wasn't that also the case in the parametric? I mean, our empirical was discrete. Right?
Yeah, but he's talking about the prior itself seems to always give you discrete distributions. And if you believe the true distribution is continuous, maybe you don't want to use a prior that gives you discrete. But because it's dense, people don't worry about that. There are ways to get continuous things, though. We're going to use that when we do density estimation.
What is the output of the Bayes estimator?
Well, you get the posterior mean.
Posterior, how do you get the posterior?
Oh, that was F bar. Where did I put that? This is the posterior. I lost F bar. I erased it. But remember, I wrote down F bar. That was the posterior mean. That's the expected value of F given the data. And you have the whole posterior in the sense that you know how to draw random samples from the posterior. So you can construct a Bayesian confidence band. You can get the posterior mean. You have all the information you want.
What do you mean by dense? Is that from the prior usual large number of samples from the...
Now what I mean is that the support of the distribution, which is where this prior puts all its mass, that support is dense in the space of all distributions.
Does it have anything to do with the number of data that you have sampled?
No, this is just a prop. This has nothing to do with data. This is just a property of the Dirichlet process.
Your F naught need to be continuous,
F naught does not have to be continuous.
but to get a dense support everywhere.
Yeah, actually, I think that's true. You're right. So I think I have to restate it. If F0, that sounds right. If F0 is fully supported on the real line, then I think the support of the Dirichlet process is the set of all distributions.
How can we define expectation on function value random variable?
This is defined point-wise, so I can define it this way. Okay. For people who are used to dealing with these things, and I think some of you have, this is all kind of second nature, but if you've never seen it before, I realize it all seems a little bit odd because we're not used to dealing with random functions and so on. Any other questions about the Dirichlet process?
How do you calculate the mean of infinite dimension?
Oh, you do it because I gave it to you. I gave you the mean. You mean how do you prove that's the mean?
Yes.
Well, I'm not doing the proofs. I mean, these go back to Ferguson's original paper. So actually, that's probably the best reference. If you want to see how these, how these properties are proved and so on.
I even don't know what's the probability space is defined on
Well, it's the set of all distribution functions.
but if you take the mean, you will use a matter space. Where do you put the probability of?
Well, the way to think about it is, this is the set of all CDFs. I know my drawing isn't so great, but this is the set of all CDFs. And we're putting a prior on here. Then we get data, and we have a posterior here. So there is a mean. This distribution has a mean somewhere, F bar. And the formula, which I erased, is it's a very explicit formula for that mean.
But this is one-dimensional, right? It's on R.
I'm still dealing with R only. Real valued random variable, but the objects are CDFs on R.
Do we always consider all possible distribution functions?
No, when we get to density estimation, things like that, we can't. We won't get well-behaved things anymore.
I mean, can we use some subspace here?
If you want to, I mean, the idea of being non-parametric, and we'll get to this when we talk about, we're going to eventually get to how do we show these things are consistent, or are they consistent? To have a consistent non-parametric Bayesian procedure, we need to make sure we put mass all around the space in some sense, in a sense that I'll describe. If you leave out big pieces of the space, and if the truth happens to be there, then you're not going to get a consistent estimator. So, and we'll talk about that when we talk about consistency. But the goal of nonparametric inference is that we don't want to usually ahead of time rule out parts of the space. Now you might want to in some cases, right? You might say, I have some information about the shape of f, and you might want to restrict it to CDFs with certain shape restrictions. So there are cases when you might want to put in extra constraints. But this is the basic vanilla way of doing it. All right, so any other questions? So that's all the detail I want to do because there are whole courses again about this topic that covering fascinating questions. But I just want to make sure you understand what the prior is, that it's something well-defined, that it leads to a well-defined posterior, and we can compute the posterior mean, and we can draw from the posterior. It's all well-defined object. Okay? Did I?
Just to be clear, the posterior is also discrete. Right?
Yeah, the posterior, if you draw from the posterior, you will get a discrete distribution with probability 1. That's correct. Okay. So that was the easy one. Because now, we're going to talk about density estimation. This would not be a good prior to use for density estimation because when we draw from, take a typical draw from the prior, I get a discrete distribution. It doesn't even have a density. So densities, the set of densities is the object we're interested in. These priors aren't sort of friendly to that. So we need to make sure we have a prior now in the set of density functions, not in the set of CDFs. So remember that I have a reminder in the notes, but I'll just say that the typical frequentist way would be compute something like a kernel density estimator, just so you remember. But now what we want to do is take a Bayesian approach. One approach, which some people still use, is to use like a mixture of normals. So you take a mixture, or more generally a mixture of parametric so you would have like a weighted mixture. These are parameters. They're numbers that sum to 1, and they're treated as parameters. These are parameters. So like in the normal case, theta j is actually a mean and a variance. But also, the number of things in the mixture is also a parameter. That's what makes it non-parametric. If I fixed k, it's a parametric model. But if I let k have a prior and let it be any number, then it becomes more like a non-parametric model. And there's quite a lot of literature about using models like this. You have to put a prior on this, a prior on these things, and a prior on these things. There's sampling methods for computing the posterior. These were popular for a while, but then they kind of fell out of favor, I would say, and are replaced by what are called, what we're going to talk about, which is a Dirichlet process mixture. Intuitively, it's going to just replace this with an infinite mixture. Instead of having to specify we're going to use effectively an infinite number of things. And let me just say what the basic model is. Okay, so I'm going to describe the prior again in the same way. Well, I want to describe, in fact, how you would draw from the prior and how you would then draw an observation from the resulting distribution. I'm going to give a complete description of the joint distribution, which is called a Dirichlet process mixture. But before I do that, the basic idea is that when you have a mixture, these things are smooth. This would be like normals. But the centers of the normals, just think, that's just say, like if you have a mixture of 4 normals, and say these are the means, there's just 4 numbers there, right? You can think of those thetas, if we're thinking in a Bayesian way, they're random draws from something. But it's a discrete thing, right? The centers are like a discrete distribution. That's exactly what the Dirichlet process gives us, discrete things. So we're going to use the Dirichlet process not to think about at the fundamental level of the distribution, but at a higher level for drawing the centers of the things that we're mixing. So it's going to look like this. Let me describe the whole joint distribution. We imagine we're going to draw a random distribution from a Dirichlet process. So there's 2 hyperparameters, alpha and f0. Okay. Now in practice, people usually put a prior on this, hyperprior. And this f0 is usually taken to be something like a normal, which itself has parameters in it, which are itself giving priors. So there's lots and lots of layers in practice that are used here. But just to keep it simple, imagine that the first part of the prior is I'm going to draw a random distribution from a Dirichlet process. Now what I'm going to do is draw theta 1 to theta n numbers, from this distribution. We'll write it this way. So I'm constructing, again, if we think about a mixture of normals, and I'm just taking the centers of the normals, I'm giving you a way to draw from the prior. And the way I'm doing it, I'm going to draw n numbers from this randomly drawn distribution. But think about what happens. What does f look like? F is discrete. So it's going to have like some mass here, some mass here, some mass here. And actually, you know, remember it had infinitely many pieces of discrete mass, but many of them are small. If I just look at the big ones, you know, the first 10 of them or something like that, it's going to look something like this, then a bunch of small ones. So when I draw a theta from here, I'm going to draw from this distribution. Then I'm going to draw a second time, draw a third time. Because it's discrete, I'm often going to draw the same one again. There's a high probability, or non-trivial probability, that I could draw this point multiple times. So in other words, even though I'm drawing n points from here, they need not be distinct. In fact, typically they will not be distinct. And this is a good thing because this is capturing the idea that if you think about doing nonparametric density estimation as using a mixture of normals, I want lots of observations to come from one normal. I want lots of observations to come from the second normal. I want clustering to occur. What's happening is this is creating clustering. It's causing a lot of the thetas to be the same, which is like saying that a lot of observations are going to come from one normal and a lot of observations are going to come from another normal. In fact, now I'm going to draw, the final thing is what's the model? The model for the data is that, I called it x here, is that xi given this is going to be drawn from. So just to give you a concrete example, I might end up getting theta 1 might be equal to theta 2, might be equal to theta 3, and they're all right there. And then maybe theta 4 is here, maybe theta 5 is here, then maybe theta 6 is equal to theta 7, and so on. And so if you imagine, when I draw x1, x2, x3, well, x1, x2, x3 are all going to be drawn. That's like saying I'm drawing them all from this common normal. This one's drawn from this normal, this one's drawn from this normal, this one's drawn from this normal. I'm getting a mixture of normals. So we're using the discreteness of the Dirichlet process to our advantage. It's creating this kind of cluster structure.
So I suppose we basically do the same thing again to sample another parameter for these component distributions, but is there any point to doing that? Or
We could, sorry, say that again?
so here, right, we're varying the means of these.
Yeah, actually, it's not just the means. It's all the parameters in here. So typically, this will really be a vector. I just said means to keep it sort of conceptually simple.
So f can't be non-parametric.
F itself is going to be parametric. But because we're forming this potentially infinite mixture of them, the resulting, so if you think about the typical density I get now from this, like I just drew, this is a way, again, of drawing. So I could imagine repeating this process over and over and drawing these densities. I'm giving you an algorithm again for drawing from the prior. You're going to get different densities every time. You're getting a distribution over densities, but you're guaranteed to get a density. And it's non-parametric because it isn't, a mixture of normals doesn't look like a normal, right? You're going to get all kinds of different things.
So for the variances, you also have another DP, or do you have a way to couple these two things together?
You do them together simultaneously. So this is going to look like this. Well, actually, let me think about that. Do people usually do them together or separately? I think you can do it both ways. I've kind of forgotten what the most common method is. But you do need to have something going on for all the parameters.
But the DP is over R, so how can you get?
Yeah, so that's why I'm wondering whether, let me look at I think I have a specific example. I mean, you can just take the stick breaking process and plant the seeds in R2 or R3. You can, make it work on any dimension, actually. So this is a little bit, I know it seems a little bit Baroque, but it's a well-defined process again. And so we can talk about the prior kind of indirectly, but think about drawing random densities this way, and this is describing the prior. Now, for the posterior, again, we can't write it down in closed form, but there are methods for doing MCMC. That is, for drawing random densities, as many random densities as you want, from the posterior distribution. It's kind of complicated now. It's not as simple as the Dirichlet case. Okay, there's a lot of steps involved, and this is not a course in MCMC, so I'm not going to go through all the details. I have a little bit about it in the notes, but really, I don't want to cover that in detail. You just trust me that just like in the Dirichlet process case, we don't write down the posterior, we just sample from the posterior. And here you sample from the posterior, and it's just a more complicated sampling process. So what would you get at the end? Well, you could draw many samples from the posterior. So what are you going to get? You draw the first time, you're going to get some density. Draw a second time, you're going to get a different density. Draw a third time, you get another density. So you're going to get, let's say 10,000 draws from the posterior. You can get a point estimate by just averaging these. That would be the posterior mean. You can get a confidence band by just counting, putting a band that contains 95%. So although it's not quite direct in the sense we can't write down simple formulas like for a kernel density estimator, the procedure is still perfectly well defined. We have a procedure for defining the prior, and we have most importantly, we can draw from the corresponding posterior distribution. Now, the real ones are quite complicated because, as I said, the truth is people don't want to specify an alpha. That they feel too locked in. So they put a prior on alpha. That prior is usually something like a gamma distribution, which itself has parameters that you have to pick. And then F0 typically is specified to be, maybe they'll guess some sort of normal as a, but then you have to put a prior on this and a prior on this. So there's many levels. It's a multi-level model, which makes, there's a lot of parameters to specify the prior, and there's a lot of tricks to use to do the posterior sampling. It's getting a little bit more complicated. But so that I don't want you to lose the conceptual framework, which is really, it's the same as before, is our parameter space is now just, instead of I know my drawings all look the same, so it looks like the set of CDFs, but this is actually the set of all density functions. And somehow we've now constructed a prior on the set of densities, and there is now a well-defined posterior on the set of densities. And we can't write it down, but we can sample from it. So it's the same framework.
Is there no closed form for the posterior mean?
No. Yeah, this is getting a lot more complicated. The really interesting question for us in this class, I think, which is what we're going to probably have to go, I guess, till next week, is how does the posterior behave? It's one thing to just do this and run an MCMC, but we should, and I have no objection to that, but I think it is something we should all think about when we do this, is what are the properties of the corresponding posterior? Is it consistent? Is it minimax? Does it contract at the minimax rate and so on? And we're going to see there's some surprises there. It turns out consistency is pretty easy, but when we start talking about minimax rates and like frequentist coverage, there's some really, really weird things going on. But we'll get to that next week. I want to describe the very last problem. Do we have time to do this? Let's see. It's 10 minutes. Let's give it a shot, which is regression. So typically what's done in nonparametric Bayesian inference for the regression function. So what did we do for frequentist? Local polynomial, kernel, whatever. Okay, here, same game. We need to put, well, actually, there's two unknowns, which is the distribution of epsilon and this thing m. People just typically assume this is normal. So that solves that problem. The hard problem now is how do I put a prior in the set of regression functions? So again, we're going to describe the prior that people typically use by describing its properties. Just like I said, a Dirichlet process has the property that on a finite partition it has a Dirichlet distribution. We're going to say that M is a Gaussian process. Let me use the same notation. Did I have it? I don't even think I put a notation here. Well, I'm going to call it GP for a Gaussian process. What does that mean? So what does it mean? Again, imagine that somehow you can draw from this process. So it's going to give me a random function. What does it mean to say that this has a Gaussian process? All it means is that if you pick any finite set of points, let's say here, 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 and here, and I look at these values, so I look at the value of the function here, 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 so that gives me a vector, that has to have a Gaussian distribution. Okay, so this is going to be normal with mean given by, this is a function, mu, this is the mean function. We just evaluate it at these points. And this is a function of two variables, essentially a kernel. But if I evaluate it at this finite set of points, I get a matrix. So to say that something is a Gaussian process only means I have a random function with the property that if I were to evaluate it at any finite set of points, the resulting vector would have a normal distribution. In fact, you can think of how to simulate from this intuitively is just pick a fine grid of points and just now you've discretized the problem, you've turned it into a finite problem and just draw a normal random vector. And that's going to approximate this random function. So it's just like a high dimensional normal, basically.
So you mean the vector mx1 to mxk is following a multivariate Gaussian distribution?
Correct.
We sample different functions m.
This is for if I draw a random m and evaluate it, and now repeat this, the resulting distribution is a Gaussian, yeah. Yeah.
And what is the covariance operator?
Well, so this covariance operator is just a function of two things. And when you evaluate it on any finite set, you get a covariance matrix. But this is what you have to specify. And so when we do kernel regression, we have to specify a bandwidth to control the smoothness. Here you have to specify this whole function. So there's a bit more to specify. That's another thing I should have said. You know, in the density estimation case, we only had to specify a bandwidth. In the Bayesian approach, there's about 73 hyperparameters you have to specify or something. I don't know how to pick them. You know, maybe people who are good at doing that know how to pick them, but I don't know how to pick them. It's the same here. We have to specify, it seems, a bit more. We have to because this covariance thing controls the smoothness of the function. How? If I make things that are close together have very high correlation, you're going to tend to get smooth functions out. But if I make them very uncorrelated, you're going to get bumpier things out. Typically, people pick covariance kernels, as these are called, that are parameterized by certain parameters, and then you put priors on those parameters. That's how it's usually done in practice. And we're running out of time, but I just say that it's a straightforward calculation now to show that if I have a normal likelihood, like a normal error, I put a normal process on here, the posterior is normal. I mean, you can just think of doing this on a finite, pick any finite set of points. It's the normal calculation. And so M, given the data, the posterior, is also a Gaussian process. And here's the punchline. If I compute the mean of that Gaussian process, I get, and the calculations are here on page 11. I just want to give you the final answer that the posterior mean, given the data, here's what it turns out to be. It's that this is the kernel matrix. Times the data. It has a very simple form. This is just from the usual normal calculations. Okay.
So why is the difference between the regression case and density estimation?
Because if I did this for density estimation, I'd have a problem. I don't get densities out. This is easier because the regression function can be any function, but densities have to be non-negative and integrate to 1. So, but
for the parametric like form, it also both use the kernel smoothers. So what's the difference between the non-parametric case and parametric case?
for density estimation?
Yeah, for density estimation and regressions, if we are using the parametric estimation, we can both use the kernel smoother rate, but they are uniform in that case. But in the non-parametric work, for one thing we use like the Gaussian process, and for the other thing we use like the Dirichlet process. So why a difference occurs here?
Why do we use different prior structures?
Yeah.
I think it's just what turned out to be convenient to work with in each case, probably. Maybe history. Yeah. And again, there's lots of other priors you could use, and people do use other priors, right? I'm just describing what I think of as the most common ones. Let's look at the posterior mean. Does this look familiar? That's a linear estimator. Remember we saw local polynomial, blah, 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 all the things often turned out to be something, a matrix times y.
Where's the data capital X and small x?
They're in the kernel. They're hidden in there. But the point is you're getting out something very similar to a kernel estimator. It's another linear estimator. Yeah.
Is this a point-wise expectation?
Yeah.
A particular x?
You're right. I meant that to be evaluated at the data points, actually.
The kernel, you mean you put the data point here.
Right. This is all. Sorry, I was a bit quick about this.
Small x. Where is the
Yeah, this is the kernel evaluated at the observed x's.
where is the small x up here? You want this to be the result of the mx.
Yeah, just to be clear, I'm actually only telling you what the mean of this is, evaluated at the actual x's for simplicity. Okay? And this kernel is only evaluated, this covariance thing is a covariance matrix evaluated at the observed x's. Everything here is evaluated at the data, just to get this expression. So where are we? So in principle, I hope I've convinced you that there are ways for CDFs, for density estimation, for regression functions to specify a prior in some meaningful way on those space of functions and to somehow get access to the posterior, either by being able to write down the posterior mean in closed form or at least being able to describe how to sample from the posterior. And there, again, this is a huge topic. I sound like Donald Trump. Huge. Huge topic. And I've been watching too many political shows. But it really is a huge topic. And so there's tons of stuff out there. I don't want to get into all the nitty-gritty details of all the methods, which are interesting, especially how to sample from these things. Can be very tricky and takes a lot of ingenuity. What I want to talk about, and it'll be next Tuesday, now are what are the properties of these things? This doesn't get talked about a lot, but when are these things consistent, minimax, and so on? Okay, and so remember, Thursday we'll be boosting, and then Tuesday we'll finish this subject off. Any questions before we break? Yes?
When
Yeah, you could. So could you create a Gaussian process mixture? Sure. You could. You could mix and match these things, and you can be very inventive and create other things. It's very problem specific, though, right? I mean, usually people create different versions of these things or different priors to deal with a particular problem. Document classification is a perfect example where people deal with very complicated mixtures of Dirichlet's, for example, to deal with word counts and things like that. But yeah, you can create lots of variations of these things. All right, so try to be on time for Sivaraman's lecture, because he's a lot meaner than me.